Bienvenidos a la segunda parte de la clase correspondiente a la unidad 8 de Impulsión de fluidos. Las preguntas que vamos a intentar responder en este video están relacionadas a lo que vimos en el video anterior. En el video anterior, si no lo vieron, les recomiendo que lo vean antes. Desarrollamos la clasificación más general de tipos de bomba. Vimos que había bombas del tipo dinámicas y de desplazamiento positivo. Lo que vamos a hacer en este video es desarrollar cuáles son los diferentes tipos de bombas de desplazamiento positivo que tenemos en mayor profundidad y luego enfocarnos en los tipos de diseños de bombas centrífugas que pueden encontrarse. Como vimos en el video anterior, hay dos grandes grupos de clasificación de bombas. Por un lado tenemos las bombas dinámicas y por otro lado tenemos las bombas del tipo de desplazamiento positivo. Ahora lo que vamos a hacer es avanzar en los distintos tipos de mecanismos de funcionamiento para los dos grandes grupos de bombas de desplazamiento positivo que vimos anteriormente, que eran las bombas del tipo alternativas y las bombas del tipo rotativas. Así que ahora vamos a ver un video donde se describe en detalle cómo es el principio de funcionamiento de los 9 tipos de bombas de desplazamiento positivo que tenemos. 3 del tipo alternativas y 6 del tipo rotativas.
Hi, I'm Adam. This is the MachineTech video blog, and today I'd like to talk a little bit about the different types of positive displacement pumps. At first glance, there seem to be so many unique designs of positive displacement pump that it can be a little confusing. And it really wouldn't make a whole lot of sense to try and cover every single possibility in this one video. But what I have tried to do is to break it down into 9 basic mechanisms. At the heart of any pump, you'll find one of these mechanisms. I've also tried to show a real-world example of each different type of pump. Each basic mechanism falls within one of 2 categories based on what type of motion it utilizes. We have reciprocating and we have rotary. Reciprocating pumps are the first category. Every reciprocating pump utilizes some kind of expanding and contracting chamber and a series of check valves in order to draw fluid into the pump and then direct it out into the system. To illustrate this concept, let's take a look at pump number 1, the piston pump. The mechanism consists of a reciprocating piston inside of a cylinder with check valves at both the inlet and the outlet. When the piston is on its suction stroke, which is the upstroke in this case, the chamber inside of the cylinder expands, the pressure drops, the check valve on the suction side opens, and fluid is admitted through the inlet. By definition, check valves permit flow in one direction only, so they help to prevent backflow and direct the fluid through the pump. As the valve on the suction side of the pump opens, the valve on the discharge side closes. On the discharge stroke, which is the downstroke here, the piston pushes on the fluid in the cylinder. The pressure rises. The suction valve now closes and the discharge valve opens to release fluid into the system. Here's an example of a common piston pump called an axial piston pump. This pump is a tad more complex than our little demonstration, but the pumping action is generated in exactly the same way. The axial piston pump has multiple pistons equally spaced on the end of a rotating angled plate. As the plate rotates, the pistons are driven into and out of their respective cylinders. You can clearly see the motion here. Like most reciprocating pumps, piston pumps are relatively efficient and they're capable of generating very high pressures. Pump number 2 is the plunger pump. Plunger pumps look very similar to piston pumps, but they work a little differently. Unlike a tight-fitting piston, a plunger fits loosely in its cylinder. Just like when your bathtub overflows because you filled it too full with water before jumping in, The physical mass of the plunger alters the size of the chamber and displaces the fluid. This is a triplex plunger pump, which uses 3 staggered plungers for smoother flow delivery, but it is otherwise the same as our demonstration. Pump number 3 is the diaphragm pump. Unlike a piston or a plunger, an elastomer diaphragm is flexible. When it flexes, it changes the volume of the chamber, causing fluid to be drawn into or pushed out of the chamber. Our example is an air-powered double diaphragm pump. The pump is essentially 2 diaphragm pumps oriented back-to-back with the diaphragms linked by a connecting rod, so it can pump on both strokes. One unique property of the diaphragm pump is that it doesn't require a seal, because the wet and dry sections of the pump are completely separated by the diaphragm itself. The second category of positive displacement pump is the rotary pump. All rotary pumps utilize some kind of a moving chamber that traps fluid and carries it from one side of the pump to the other side. To illustrate this concept, let's look at pump number 4, the gear pump. Actually, this configuration is more properly called an external gear pump. The mechanism consists of 2 rotating gears, one driving the other, inside of an oval housing. At the suction inlet, fluid is trapped in a chamber between the gear teeth and the inside wall of the housing. The rotary motion moves the chamber from one side of the housing to the other side, and as the gear teeth rotate back into mesh, the chamber is closed, forcing the fluid through the discharge outlet. Another configuration of the gear mechanism is the internal gear pump. In this type of pump, an outer gear in a circular housing drives an offset inner gear. The gears are separated by a crescent. Fluid is trapped in one of 2 moving chambers, between the inner gear and the crescent, or between the outer gear and the crescent. As with the external gear pump, the rotary motion moves the chamber from one side of the housing to the other side, and as the gear teeth rotate back into mesh, the chamber is closed, forcing the fluid through the discharge outlet. Pump number 5 is the lobe pump. Lobe pumps function very similarly to external gear pumps, but the rotors are driven independently by external timing gears. The rotors have 2 or more lobes, and the moving chamber is formed between the outer surfaces of the lobes and the inside wall of the oval housing. As one of the lobes rotates back toward the center of the housing, the tight clearance between the lobe and the other rotor closes the chamber and forces the fluid through the discharge outlet. Pump number 6 is the vane pump. A vane pump rotor has slots in it for sliding vanes. Centrifugal force flings the vanes out to contact the inside wall of the circular housing, forming a sealed chamber. Since the rotor is offset in the housing, the vanes extend and retract during rotation. The chamber increases in size at the suction inlet, drawing fluid in. At the discharge outlet, the chamber decreases in size, pushing fluid out. The nice thing about vane pumps is that they automatically compensate for wear because the vanes are constantly forced against the wall of the housing. Pump number 7 is the peristaltic pump. Peristaltic pumps contain fluid within a flexible hose. The hose is pinched between the rollers and the inside wall of the housing. As the rollers revolve around a center axis, they squeeze the fluid like a tube of toothpaste and move it through the housing to the discharge outlet. As with diaphragm pumps, peristaltic pumps do not require a seal because the fluid's completely contained inside the hose. They really excel at pumping high viscosity fluids with very large solids. I've even seen them pump whole cherries without significantly damaging them. Pump number 8 is the screw pump. Screw pumps can have a single shaft with large threads on it, but they usually have 2 or 3. The center shaft drives the other shafts like a screw or a worm gear. As the shafts rotate in the housing, fluid trapped in the gaps between the screw threads progresses along the length of the housing and is delivered to the discharge outlet. If you've ever seen an auger or a screw conveyor, this is pretty much the same thing. Our final pump is pump number 9, the progressive cavity pump. These bizarre little pumps may look somewhat like screw pumps, but they function differently. The rotor is shaped like a helix, and the housing is molded into the shape of a double helix. As the rotor rotates and oscillates inside of the housing, it forms a cavity which progresses along the length of the housing. Any fluid trapped in this progressing cavity is delivered to the discharge outlet. Well, there's your introduction to the various different mechanisms that make up the positive displacement pumps. And that's it for today from the Machine Tech video blog. I hope you learned something.
Bien, como vimos en el video anterior, dentro de las bombas alternativas tenemos 3 mecanismos de funcionamiento. Pueden ser bombas de tipo pistón, de tipo émbolo o de tipo diafragma. Por su lado, dentro de las bombas de desplazamiento positivo de tipo rotativas, tenemos otros 6 tipos de mecanismos de funcionamiento, que pueden ser por medio de engranajes, por medio de lóbulos, paletas del tipo peristálticas, del tipo tornillo o por último del tipo de rotor flexible. Como vimos en el video, por el tipo de funcionamiento que tienen las bombas alternativas, presentan caudales de tipo impulsivo, ¿sí? Son impulsos porque hay un tiempo que destina a llenar ese volumen que es utilizado para impulsar el fluido. Bien, entonces lo que se adelanta en el video es que hay distintas alternativas que permiten minimizar esos picos y valles en el caudal. Bombas de acción simple, sencilla, sería el caso más básico, en donde se generan impulsos. Una alternativa es o bien poner 2 pistones desfasados que compensen cuando uno está llenando, el otro se está vaciando, o bien hacer que con un solo pistón que se llene de ambos lados. Entonces, mientras un lado se está llenando, el otro se está vaciando y entonces permite compensar esos picos y esos impulsos de fluido. Por último, la tercera alternativa es ya poner 2 pistones que a su vez cada uno se llena mientras se está vaciando y a su vez están desfasados, permitiendo compensar de la mejor manera posible y lograr un caudal más estable. Esto se puede ver con más detalle en este gráfico. El más básico, el simplex de una sola acción, tenemos el pistón se descarga, se llena, se descarga, ¿sí? Tenemos caudal, sin caudal, caudal. La siguiente alternativa es decir, bueno, o bien que cuando se está descargando ya se estuvo llenando del otro lado, entonces cuando vuelve compensa. O tener 2 pistones separados. Cuando uno se está llenando, el otro está descargando. Entonces anulamos este tiempo muerto en donde se está llenando el volumen. El más complejo, que permite estabilizar cada vez más el caudal, es tener 2 cilindros desfasados que cuando uno se está llenando, el otro se está descargando, pero a su vez cada pistón, mientras se está descargando, se está llenando. Entonces, de esa manera compensamos y logramos tener un caudal, si bien no es constante, porque también tiene picos y caídas, nunca pasa por el cero, ¿sí? Levantamos en lo que antes teníamos el punto mínimo era en 0, cuando terminaba uno de los ciclos y comenzaba el siguiente. Ahora, al estar desfasados en medio ciclo, lo que antes teníamos como 0, ahora tengo caudal. Entonces permite mantener un caudal que, repitiendo, si bien no es constante, nunca pasa por el 0. A su vez, dentro de las bombas rotativas de engranajes teníamos 2 alternativas, con engranajes externos o con engranaje interno. Ahora, al igual que hicimos con las bombas de desplazamiento positivo, vamos a desarrollar en mayor detalle las bombas del tipo dinámicas, en particular las bombas centrífugas. A continuación vamos a ver un video en donde se describen los distintos tipos de bombas centrífugas y sus variantes de diseño.
Hi, I'm Adam. This is the Machine Tech video blog, and today I'd like to talk to you a little bit about the different types of centrifugal pumps. When it comes to pumps, most operators only care about inputs and outputs. How much pressure does the pump generate? How much flow does it deliver? How much power is required to run it? But maintenance people need to know a few more details about the inner workings of these machines if we're going to be on the hook to keep them in good running order. We don't have time to cover the specifics of centrifugal pump operational theory here, but it was the topic of a previous video. Just as a refresher, centrifugal pumps get their name from the way they impart energy to fluid. When fluid enters the pump, it comes into contact with the rotating impeller and is thrown outward by centrifugal force. It travels through a specially shaped chamber called a volute and exits the pump at the discharge outlet. All centrifugal pumps share this basic operating principle, but there are a few possible variations among them. There are 5 primary design elements to consider: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. There are a few special designs as well, but those will have to wait for their own videos. There are 3 types of impeller: open, semi-closed, and closed. The simplest impeller construction is the open impeller, which consists of nothing more than a few curved blade-like vanes equally spaced around a hub on the rotating pump shaft. Large, unrestricted fluid pathways allow this type of impeller to pump fluid containing mud, leaves, twigs, sand, sludge, spray paint caps, dead birds, you name it. And that makes them ideal for trash pumps or this pump, which actually came out of a wastewater treatment plant where it was pumping raw sewage. It was necessary to handle gritty slurries with soft solids. And it even has special chopper blades just ahead of the impeller to help break down very large solids. Ooh. If the vanes are mounted on a backing plate called a shroud, then the impeller is a semi-closed impeller. And if the vanes are sandwiched between 2 shrouds, then it's a closed impeller. Closed impellers are more efficient than either semi-closed or open impellers because the fluid is directed through very well-defined pathways. That means that more of the fluid is pumped out into the system and less of it is just recirculated around and around and around inside of the pump. Of course, the trade-off is that they can very easily get clogged with debris. Whichever style of impeller is used in a pump, it's mounted on a rotating shaft and needs to be supported by bearings inside of the casing in one of 2 ways, either overhung or between bearings. In an overhung configuration, the impeller is cantilevered on one end of the shaft and the bearings are offset to the other side. This configuration places the suction and discharge piping at 90 degrees to one another, with the inlet directly in front of the suction eye at the center of the impeller. This is why pumps with overhung impellers are more commonly referred to as end suction pumps. End suction pumps are abundant in industry because they're relatively cheap and easy to manufacture, but they do have one big disadvantage arising from the way that fluid travels through the pump. During operation, there's a zone of low pressure at the suction eye where fluid first enters the impeller, and a zone of high pressure at the outside rim of the impeller where the energized fluid is released into the volute chamber. This high-pressure fluid also has a leak path to the backside of semi-closed and closed impellers, which totally throws off the balance of pressure. The net effect is a constant axial force, or thrust load, pushing the impeller toward the suction inlet of the pump. You can compensate for this effect a little bit by installing beefier bearings capable of handling thrust loads, or drilling holes through the impeller shroud to allow for some pressure equalization. But neither of these are true fixes for the problem. A more effective solution is presented if the impeller is supported by bearings on both sides, called a between bearings configuration. Not only does supporting the impeller with bearings on both sides generally improve shaft support, it also means that many of these pumps can employ symmetrical closed impellers with double suction. Since there are identical low and high pressure zones on both sides of the impeller, this effectively eliminates thrust forces due to pressure imbalance. And this design has another key advantage. The suction and discharge piping are normally positioned parallel to one another on opposite sides of the pump, and the casing is split axially so that just by removing some bolts and pulling the cover off, maintenance technicians can access the rotating assembly inside the pump without removing the whole pump from the system. This axially split design is why pumps with impellers between bearings are more commonly referred to as split-case pumps. Now, those are all pretty convincing reasons to go run out and get yourself a split-case pump right now, but of course there has to be a disadvantage. Because the manufacturing processes and the sealing requirements for split-case pumps are much more elaborate than for end suction pumps, they're also naturally more expensive. Next on the list of design elements is orientation, either horizontal or vertical relative to the pump shaft. Centrifugal pumps are usually oriented horizontally, but they can also be oriented vertically. Vertical pumps are used in plants where a reduced footprint and space savings are desirable. And you may also find one down at the bottom of a well or sump connected through a long line shaft to the driver above. This brings us to the mounting method of the driver, usually an electric motor. There are two options for transmitting rotational force from the driver to the pump, either frame-mounted or close-coupled. If the pump and driver are two separate units, as they are here, then the pump and driver shafts will need to be connected by some type of a coupling. Now, couplings come in all shapes, sizes, and styles. But one characteristic common to all of them is that they require proper alignment of the shafts, and that can be a very finicky process indeed. To help facilitate and maintain machine alignment, the pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame-mounted. For large, heavy equipment and for all split-case pumps, frame mounting is really the only way to go. A second option is the close-coupled mounting method, in which the pump and its driver share a common shaft, with the impeller mounted overhung on one side of the driver shaft. In this case, there is no need for a coupling or any of the extra labor required to perform sensitive alignment procedures. However, since both the pump components and the driver components are supported on the same shaft just by the bearings in the driver, this mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps have one stage with a single impeller and a single volute chamber. However, some pumps have additional stages connected in series to help boost the pump's discharge pressure. The idea is that the first impeller adds energy to the fluid and then feeds it into the next impeller, which adds more energy to the fluid, then feeds it to the next impeller, and so on and so forth until the fluid is eventually discharged into the system. Well, there's your introduction to the different classifications used for centrifugal pumps: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. And that's it for today from the Machine Tech video blog. I hope you learned something.
Retomando lo que vimos en el video y resumiendo, los tipos de bombas centrífugas pueden clasificarse según el tipo de impulsor, que puede ser abierto, semiabierto o cerrado, la configuración de rodamientos, que puede ser del tipo voladizo con la succión al final, o entre rodamientos, que suelen llamar de carcasa partida. Por la posición, horizontal o vertical, y dentro de las verticales puede ser o bien en seco o sumergida. Por el montaje de la transmisión, que puede ser de bancada o monobloc, y por el número de etapas, que puede ser simple o múltiple. Lo que no aparece en el video, hay dos tipos de bombas que podemos agregar, que puede ser por tipo de flujo, que puede ser radial, axial o mixto. Todos los que se ven en los videos son del tipo radial, pero tenemos la opción de que el flujo sea axial, ¿sí? Observar que en este caso es como entra por el ojo del impulsor, pero en vez de salir de forma radial, sale de forma axial, como si fuera una turbina. Observar que sigue el eje axial del impulsor. o de flujo mixto, que es una combinación de ambas. ¿Sí? Tiene una componente radial y una componente axial. Y por último, también puede ser por tipo de caja, que es de caja voluta, que es la que venimos viendo, o de caja con difusor. ¿Sí? De caja voluta es lo que veníamos viendo, tenemos el impulsor y en ambos casos el objetivo, como habíamos visto, en este caso particular de la caja voluta, es ir ganando sección de flujo para que toda la energía cinética, toda la velocidad que se ganó dentro del impulsor sea convertida en energía de presión. En la caja con difusor también se va ganando sección para que la energía cinética se traduzca en energía de presión. Si resumimos o hacemos una comparación en cada una de estas clasificaciones, dijimos que los tipos de impulsores podían ser abiertos, que tiene la ventaja de tener la posibilidad o la capacidad de impulsar fluidos con sólidos en suspensión, y en caso del impulsor cerrado son más eficientes, pero obviamente no tienen la posibilidad de impulsar fluidos con sólidos en suspensión. En función de la configuración de rodamientos, el voladizo es más barato, más fácil de fabricar. En el caso de entre rodamientos, tiene un mejor soporte del eje para minimizar vibraciones, permite utilizar impulsores simétricos con succión doble, como en este caso, ¿sí? Que a su vez reducen el AMPA requerido y minimizan la posibilidad de cavitación. Y la otra ventaja que presentan es que la carcasa se separa axialmente, por lo que permite, simplemente levantando la tapa, se puede acceder a las partes móviles para hacer mantenimiento. Mientras que en el caso de voladizo hay que desmontarla completa para poder acceder y realizar el mantenimiento o la lubricación. En cuanto a la orientación del eje, dijimos que teníamos vertical o horizontal. Por un lado, horizontal tiene la ventaja de ser más baratas y más fáciles de desmontar para mantenimiento. Por su parte, las del eje vertical tienen la ventaja de que permite instalarse en espacios más restringidos y permite operar sumergida. No requiere cebado. Estas son las más típicas que se usan para bombear en pozos de agua. Y al mismo tiempo, al estar sumergida, elimina todos los problemas de succión. En cuanto al tipo de transmisión, en el caso de las de bancada, tienen la ventaja de que permiten mayor flexibilidad de tipos de bomba. Por ejemplo, se puede ser de carcasa partida o de mayores tamaños. Las monoblock tienen la ventaja de que motor y bomba comparten el eje, por lo que no requieren alineación. En cuanto al número de etapas, las simples son más baratas y las múltiples tienen la ventaja de que presentan varios impulsores conectados en serie que permiten aumentar la presión de descarga. ¿Sí? Es como tener varias bombas en serie comprimidas en una misma. Ya para finalizar este video y repasando lo que vimos, en primer lugar desarrollamos los diferentes tipos de bombas de desplazamiento positivo, ya sean las 3 tipos de bombas alternativas y los 6 tipos de bombas rotativas. Y luego desarrollamos en mayor profundidad los distintos tipos de diseños de bombas centrífugas que se pueden encontrar.